Okay, it's time to start. We have a special colloquium this week. Our guest is Dr. Thomas Bahder from Army Research Office, and he will tell us about topological quantum sensors.
Yes, with a question mark.
With a question.
Yes. Okay. I have to say, it's my great pleasure to be able to come and give this talk to you. I was born in Poland, and I immigrated with my parents to the U.S. when I was 7. But I really enjoy the trip here. So some background. I got involved in this topological in quantum sensors around 2002. At that time, there was a proposal by Jonathan Dowling that you could have these super precise quantum sensors and based on Noon states in quantum optics, and so I was working in the Army Research Laboratory in Maryland at the time for 20 years, and I was approached by this intelligence agency, IARPA, Intelligence Advanced Research Projects Agency, and they said, we want to know if these quantum sensors really exist. Can you look at this work of Jonathan Dowling and do the calculations and tell us whether it's real or not? So this is what you'll hear is a kind of a work from around 2002 to the present. So I'll talk about the ideas we came up with a postdoc of mine of a quantum sensor as a quantum channel, and I'll talk about why we should use information as a metric, how good the sensor is, and then I'll introduce two toy models, a 1-qubit and 2-qubit sensors. They're toy models. They're the simplest model of a quantum sensor that you could possibly write down, and then by looking at these models, there's an analogy with topological ideas in topological band structure. And so I'll kind of review the ideas of Barre curvature and Chern number. And then I'll talk about the quantum geometric tensor and the phase transitions. And it turns out there's a phase transition that occurs in a quantum sensor in the simplest model. And I'll talk about a 1-qubit example where you can have a model based on the real or imaginary part of this quantum geometric tensor. So the idea of this kind of what I think of as a conventional quantum sensor, this is a theorist's idea. You prepare a quantum state, some initial quantum state, size 0. Then you have some interaction Hamiltonian. There's an interaction with an external field. And then out comes another quantum state, which depends on that field. And the interaction occurs only over a finite time. When this quantum state comes out, you can make a measurement. And from these measurements, quantum measurements on this state, you can get some information about phi, the field. This is a classical field, has no quantum degrees of freedom. And so this idea is basically there's a quantum channel. The field, between the field, there's a quantum channel to the measurements. So a quantum sensor is just a quantum channel. And you really want to maximize the information in the measurements that is known about the field. And so this looks like Alice and Bob and a communication theory. And so you might want to optimize the quantum sensor in terms of the initial state. And you ask what initial state produces the most information. So at that time, I decided, well, let's take an example, a real example, which could be a Mach-Zehnder quantum sensor, where you have 2 input ports, a beam splitter, 2 mirrors, a phase shifter in one arm and a beam splitter, and then you have photon number resolving detectors. So you put in some kind of a state into ports A and B. It could be like a Fock state, where you put in 1 photon here and vacuum here. It could be M photons in port A and N photons in port B. And then you count how many photons come out of each of these 2 ports, and these are the measurements. And you want to figure out from these measurements what the field is. And you could have Noon states, which at that time were being pushed as that the Noon states were the best. And I'll show you some very interesting results that Noon states are the worst, in fact, using an exact calculation of quantum optics. So the theory is just really simple. There's a probability of obtaining a certain measurement M. The M means how many photons came out of, that's 2 numbers, how many photons came out of ports C and D, given that there was a phase with some value. And there's basically a projective measurement operator that depends on the phase. You take its expectation value with in the input state. Of course, you're not interested in the probability of the measurement. You're interested in the probability of the phase. So you invert this using Bayes' rule and get the probability of the phase, given that you've made a certain measurement outcome. You've received a certain measurement outcome, and so this you can calculate the probability of a measurement outcome, and it enters here. And this is the a priori probability, that is what you know about the phase before the experiment. And if you had a good sensor, the probability distribution would be very narrow, have one peak and be very narrow, right? So this would be a very, given some measurement, this would be a very narrow function for a good quantum sensor. Now, people usually talk about two limits of parameter determination. The parameter that we're talking about is the phase. And they usually talk about the standard limit or shot noise limit, where the accuracy in the phase goes like 1 over root n. N is the number of photons or quanta in the field. Alternatively, people talk about that there's a Heisenberg limit, which would be like 1 over n. So the accuracy in phase would be much bigger. Let's say if n was 10 to the 6th, this would be 3 orders of magnitude improved. And what I'll show you is that there is no Heisenberg limit, at least in a certain sense. So here is an exact calculation of the probability of the phase for the Mach-Zehnder interferometer, given that I've measured a certain number of photons coming out of the output ports C and D. So this is the probability of the phase versus the phase. So there's for one case, for example, the dotted line, there's a large probability that the phase is in this region, or this region, or that region. The dotted line is for an input of using Fock states. I'm sorry, using noon states. Using Fock states, that's the solid line. There's a high probability of the phase being here or there. So depending on what input state you use, Fock or noon, you'll get peaks in different places. Furthermore, the widths, well, if you look at the noon state case, you don't know whether to look at the width of delta phi being the whole thing or just one of these, because there's an ambiguity of where the phase is. So really, there's no precise way of saying there's some Heisenberg limit, because you get peaks in multiple places. So you cannot characterize the distribution by a width of one peak or multiple peaks, so it's ambiguous. So really, you want to use information measures. And the information measures, that whole idea hangs really well with the idea of a quantum sensor as a channel. And the information that we're going to talk about is Shannon mutual information, where Alice sends a character through this channel to Bob. So let's say Alice sends a character A to Bob. Bob can receive A. That would be the probability that Bob received A, given that Alice sent A. On the other hand, Alice could have sent A and Bob could have received B. So there's a probability that Bob received B, given that Alice sent A, and that would be an error probability, and so on. So this experiment is described by these conditional probabilities, and there is a Shannon mutual information formula which these probabilities enter here, 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 and these are a priori probabilities, the probability of Alice sending either of these characters. So Shannon developed this in around, of course, it's very well known, 1948. We can use this Shannon information to characterize how good of a quantum sensor we have. So this is the communication analogy we just described. On the other hand, in the sensor analogy, the phase can be between minus pi to pi. It's a continuous alphabet. It's not discrete. The measurement outcomes that we measure, how many photons come out of the Mach-Zehnder interferometer, would be discrete. So, but there's no problem with this. You can still calculate the information between the continuous alphabet and the discrete. So here is the Shannon mutual information plotted versus the number of photons for noon states and for Fock state input. So here, for example, is the amount of information for 5 Fock states and a 5 photon Fock state input. And obviously the information increases with the number of photons, but for the noon states, it's really a weird plot. It sort of oscillates. And for a 2 photon noon state, the information is exactly 0. it has to do with symmetry of those measurement operators and their expectation value. So this was a very unhappy outcome because certain people were not really pleased that Noon states were really bad, as opposed you're better off using unentangled states like Fock states. So that was not a very well received outcome, and didn't make it into physical review letters. It was only in rapid communications because it was bad-mouthed. Although this is an exact result. Sometime later on, I went on to look at this idea that you could, you have to create an input state here. Experimentally, you're never sure that you've got exactly the state that you want. Also, another non-ideality of an interferometer or Mach-Zehnder sensor is that there can be losses. The photon can be scattered out or absorbed, and then also the photon number detectors can be not correct. So here, the state preparation, you might want to say, well, there's a certain probability of an input state. You're not able to exactly have the state you want, so you're really inputting a density matrix. That goes into the optical interferometer, and there's a probability of getting a state psi out, given that a state psi in came, so that's like a transfer function, and then there's a probability that you have a certain measurement m, given that you had an output state go into the detector. So this measures the quality of the detectors, this tells you about loss and scattering, and this about your state preparation. You can concatenate these three probabilities using Bayes' theorem, and I won't look at this in detail, to give you a final probability of a measurement given the phase. As an example, here's a case of a lossy interferometer, and here's the amount of Shannon mutual information versus the loss in the interferometer. And for example, a 3-photon Fock state input into the interferometer decays like this with increasing loss. 2-photon Fock state is worse. Here is a Noon state, and here is a 2-photon Noon state, which has 0 information, no matter what the loss is. So this was kind of a surprise, not very intuitive. So I've discussed that you can use Shannon mutual information, but it averages overall measurement outcomes and overall phases. That's the nature of Shannon mutual information. On the other hand, you can use Fisher information, which is basically uses an unbiased estimator. Means you have a measurement outcome and you have a function of that measurement outcome which tells you what the phase should be, your best guess. That would be Fisher information, and it's good for a single shot estimate of a quantum sensor. So to contrast the difference between Shannon mutual information and Fisher mutual information, imagine that you were going to go to the store and you're going to go shop for the best measurement apparatus, the best quantum sensor. You want to look on the box of the quantum sensor, and if you want to know for all possible cases what the best quantum sensor is, you would look for the highest Shannon mutual information on the box. On the other hand, when you go back, take that home, and you do one experiment, you would use Fisher information. So, and Fisher information gives you the variance of phi is greater. It's a bound is greater than or equal to 1 over the Fisher information. So it describes the error statistics of an unbiased estimator in a particular experimental data run. So both of these are kind of important, and I've done a lot of calculations on those for Mach-Zehnder interferometers. But more recently, I thought to myself, well, that interferometer has arbitrary number of photons in either port that you could put in, so the Hilbert space is infinite dimensional in that problem. So let's look at something very simple. Let's look at 1 qubit. This is a 1 qubit kind of a Hamiltonian, right? Lower state minus E plus E. And then I can write down a hand-waving interaction where there's a field phi with some coupling constant, which takes the lower state to the upper state, and the Hermitian conjugate, where the field phi takes from the upper state to the lower state. And so this can be written in terms of sigma minus and sigma plus matrices, and they're just off-diagonal terms here. And you can take the sum of the non-interacting qubit with the interaction Hamiltonian, and it just looks like this 2 by 2 matrix, where those are the interaction terms. You can express this as just sigma x, sigma y, sigma z, with these are the two coupling constants. This is the real part, and this is the imaginary part of this G. And this is the energy in the problem. So, this is a really simple model. It's intuitively pleasing because this is really a very simple picture of interaction. And the field phi in this model has no dynamics. The model does not have time reversal symmetry, and so it doesn't commute with the time reversal operator. And you can compute everything analytically in this one qubit model. And you can, so the picture is, I prepare the qubit in a lower state, for example. I let it interact with the external field for some time, and then I stop and I measure the qubit, what state it's in. It's either going to be in state 0 or state 1. And there's a probability of the qubit being in state 0 or state 1, which depends on the field. It depends on the interaction time and on the gap here. And so all this can be calculated analytically. And right. And what happens is, it looks like Rabi oscillations. So here's a probability of phi versus phi for the case in blue where I've measured the qubit in the lower state. That's the blue line. And so there's a high probability of the phase being here, here, or here, or here, because the blue curves peak. On the other hand, if I've measured the qubit in state 1, that would be the yellow curve. There's a high probability of the qubit, of the field having been in these positions. Now, I can calculate the Shannon mutual information here for this one qubit sensor as a function of time, of interaction. And obviously, the longer you interact, you would anticipate that you get more information. But it's not true. For example, for different couplings here, 0.1, weak coupling, medium, and strong coupling, let's look at the green curve. The information content changes with interaction time. So you don't want to interact over this time because you get very little information. You'd want to interact, say, here over that time because you get much more information. And these are oscillations in information. They are not oscillations in interference. So they're it's some kind of an interference in it, but in information. So very weird. So you might say a one qubit sensor, what are you going to get out of it? It's such a simple model. And I'll show you that you can, in fact, use this one qubit sensor to discriminate between two values of the field. If you know that the field will be one value, phi1, or another value, phi2, if you're a priori know that, then you can plot the probability of the phase being phi1, given that there's a certain measurement outcome, which can be 0 or 1. And if it's 0, it looks like this as a function of interaction time. If it's 1, it looks like that. So for example, here, let's say that I knew that I obtained a measurement 1, and then it would be 25% probability that phi is phi1, and there would be about 60% probability that phi is phi1 if I measured 0, depending on the measure. So you can use it as a discriminator. In applications, actually, that's a pretty good idea, right, for practical device. So that's just to show you that something as silly as a one qubit model can actually be a useful device. But I started thinking more recently. Well, I looked at this one qubit quantum sensor. This is the Hamiltonian, right? Now, of course, all 2 by 2 matrices can be written in terms of these Pauli matrices, but that's not the point. The point is that I've motivated it by writing an interaction which is plausible, physically plausible. That's the idea behind this. So, and then I looked at it, and it looks just like a topological K dot P theory of energy bands of Dirac or Weil semimetals, where this is the wave vector kx in the Brillouin zone, ky in a two-dimensional Brillouin zone, and m is the mass, which is analogous to the energy gap. And so the question is, can you kind of apply some topological ideas to this one qubit model that have been applied to energy band theory? And probably yes, but first, let's take a look at a 2 qubit sensor. So here's a 2 qubit sensor where now I have a qubit here at some position R1 that measures the field, and I have a qubit here at position R2 that measures the field, and I want to know simultaneously what the values of those of two fields are, right? And now, right, so the picture is the same. You prepare a state, you have some interaction Hamiltonian, which depends on two fields, and you allow the interaction to go on for a little while, and then state comes out, and you make a measurement, and you get two measurements because there's two qubits. M1 is for qubit 1, can be 0 or 1, and qubit 2 can be 0 or 1. And you want to get maximum information about the two fields. So how do you write down a Hamiltonian for a two qubit sensor? Well, you have the Hamiltonian for one qubit essentially here, and you can tensor it with the identity, plus the identity tensored with the one qubit non-interacting Hamiltonian, which is just that we saw previously. That's the non-interacting two qubit matrix. It's going to be a 4x4 matrix. And then there's the interaction Hamiltonian, which depends on the phi1 and phi2 at the fields in two different positions. And you can just write that down as the original one qubit interaction Hamiltonian at position 2, tensored with the identity, plus the identity tensored with the Hamiltonian at position 1. So you add these up, and this is just the one qubit interaction we saw previously. You add them all up, and the wave function is of course now looks like this with these constants, and it's got to be normalized. And now that you have two qubits, you can ask the question, what if you start out at two qubits in an entangled state, or what if you start out at two qubits in a product state? Which is going to be better, right? And in fact, this question was asked by management in the Army Research Laboratory, because when I started this work with that Mach-Zehnder quantum sensor, that was around 2002, nobody was interested in quantum sensors, not even the management there. They could care less. But now they start, years later, there's all this quantum stuff going on, and governments are putting money into this now. So the laboratory management wanted to know, is there a reason to have an entanglement in a quantum sensor? So this little model I drummed up for the purposes of answering that question. And so here's the answer. Here's the 4x4 Hamiltonian for the two qubit sensor, right? Just written in matrix form. And one thing is you can calculate the entropy of entanglement, and it's constant in time. So if I start out in an initial state, these two qubits, and it evolves as it interacts with the field, entanglement will never increase or decrease. It's constant. And because it's such a simple model, this is a classical field with no quantum degrees of freedom. Okay, but here are the results. Does entanglement help you in the case of two qubit sensor? So that's right. That's right. Right. So here's the Shannon mutual information versus interaction time, and when I start out the qubit in a product state, 0, 0. So qubit 1 is in the lower state, qubit 2 is in the lower state, and this is the curve of how the information increases with time. And here's qubit 1 and 2 in the 1, 1 state. It's the same curve. On the other hand, and this is just a product state also because you can factor out the 0, but this is the singlet state. Notice that you get the least information in the singlet state compared to any other state. So that means that entanglement is bad. You don't want to start this quantum sensor of two qubits out in an entangled state because you get the least information. It's a little bit like, so the singlet state is almost like a decoherence-free subspace. It's insensitive to the field. It is least sensitive to the field, I should say. It does have some information, but less than if you used other states. So that was not a happy result either. So it was not very, when I went to the Army Research Lab and I gave them these results, people were not really pleased with this because their funding was suspect, right?
My previous question, is it actually connected to the fact that they do not interact? If they do not interact, then the most information you can get from the product state. But if you have a Hamiltonian where qubits interact with each other and you want to get this, if you have a, so then I suppose the entangled states will give you an advantage.
I haven't tried that. I can't say I have tried that, but I also don't have a lot of faith in it. It's just that this is such a simple problem. You know, now that external field I mean, if you had a quantum field, yes, the entanglement would change in time. But I think that it may depend on the type of interaction between the qubits. I don't know, right? So, okay, so you can plot the eigenvalues of the 2-qubit Hamiltonian, and it looks kind of like this. This is the energy on the z-axis. This is, and the eigenvalues I'm plotting versus the coupling constants. This is that coupling constant, the real part of the coupling constant, and the imaginary part. And there's a lower band, and there's an upper band that are decoupled, and there are bands that are, they're overlapping. I'm sorry, they have a band crossing right there. This is a true band crossing. It is not an anti-crossing, no matter how close you look. So it looks just like the problems of the Dirac cones, you know. So, but the eigenvalues don't contain all the information. You really need to look at the eigenvalues. So you need to invoke some kind of topological ideas. And the most basic idea is this idea of topological equivalence, that two objects are topologically equivalent when they can be continuously deformed or transformed one into the other. For example, you can look at a sphere and you can deform it into a vase. Or you can look at a donut and you can deform that into a coffee cup. Or here's a double donut with 2 holes can be deformed into a crazy coffee cup. So, and so on. And the genus counts the number of holes in this. And that's a topological global property. An example of this is the Gauss-Bonnet formula for a closed 2-dimensional surface, a Riemannian surface manifold, which you integrate over the area of the manifold, and this is the Gaussian curvature, which is 1 over the product of the principal radii of curvature on that surface. The Gauss-Bonnet theorem says it's 4 pi times 1 minus g, the genus. For a sphere, this is 4 pi r squared is the area. This is just 1 over r squared. And it's basically gives you 4 pi times 1 minus 0. It's trivial for a sphere, but for an arbitrary closed surface, it's not so trivial. So switching gears a little bit, let's talk about the Hamiltonian, which depends on parameters. In the 1 qubit, the Hamiltonian depends on G1 and G2, the real and imaginary parts of the coupling constant. And you can make a 2-qubit Hamiltonian also depend on the same real and imaginary part. You can then talk about a Schrodinger equation where there's parameters in it, S, which n parameters, and you can start the system out in the parameter space, S1, S2, and S3, and you can move this system in a closed path. And there's a quantity that Barre defined called the Barre connection, which is for the nth eigenstate, you take the expectation value of the gradient with respect to these parameters. And that is the analog of a magnetic vector potential, but in parameter space. And it's not a gauge invariant quantity, so just like the vector potential is not gauge invariant. But now we can, Barre talked about cyclic adiabatic evolution, meaning we're going to move those parameters very slowly. And what do you get? And what he showed, I won't go through this in detail, but what he showed is the wave function basically has 2 parts. It has a dynamical phase, and then it has this geometric phase. And the geometric phase is gamma n depends on the contour that you take those parameters around, and this is the Barre connection integrated along the closed path. And this is a gauge invariant quantity, which means it's a physical observable. And what do we mean by gauge transformations? Well, you take psi, depending on those parameters, and there's a phase here, which depends on those parameters, times the original psi. Just like in E and M, this vector potential transforms the same way. This is for a case where you have 3 parameters. So, so we saw this Barre connection integrated around a closed path gives you this physical observable, the Barre phase. But you can also define a Barre curvature for the nth band, and this is the nth component. It's the gradient with respect to, it's the derivative with respect to mu of the nth vector potential minus the reverse of those. It is just like E and M. This is like the analog of a Maxwell tensor. And there's a sum rule. When you sum over all the bands n, it sums to 0. And the flux of this Barre curvature in the two-dimensional parameter space gives you the Barre phase. So that's the relationship between the Barre curvature and the Barre phase. So there's now Chern made a generalization of the Gauss-Bonnet formula for the case of two parameters, and it's useful for two-dimensional systems that have no time reversal symmetry. So this is the Barre curvature. When you integrate it in this over a two-dimensional compact manifold, you get 2 pi times an integer. In this case, it's the Chern number of the first Chern class. And an example of this is in the integer quantum Hall effect, where you have a two-dimensional electron gas at an interface, and you look at the Hall conductivity, and you integrate over the two-dimensional Brillouin zone, the Barre curvature. That quantity can be shown to be an integer times e squared over h. So that's why it's quantized. You get these plateaus of quantized conductivity. So the exact quantization of the Hall conductance was explained by Laughlin in '81 based on gauge invariance, but later it was related to the topological invariant by Thouless, Avron, and New. And so let's talk about the one-qubit quantum sensor. Here's the Hamiltonian. Again, you can calculate the Barre curvature. These are the coupling constants, the real and imaginary part for the upper and lower state, right? And you can do an integral of the Barre curvature to get the Chern number. Except in this case, you don't get you get the sine of e, but you don't get an integer. You get 1/2. It is an invariant. That is that you can move these coupling constants around, and as long as e does not go to minus e, you have an invariant. But when e changes sign, there's a sign change here, and that's a signal that there's a quantum phase transition occurring at e equals 0. So something in this simple one-qubit quantum sensor already says there's something funny going on, right? And there's some sort of deeper connections. And why this is not an integer is because the Chern number must be an integer for integrals over compact manifolds, and this was not a compact manifold. This was minus infinity to plus infinity. Okay, and so if you plot the eigenvalues for the single qubit quantum sensor, this is as a function of the gap. It just looks like that. When the gap closes, you have this looks like a Dirac or Weil point, and then it changes sign. You get something that looks like that. This is for the one-qubit quantum sensor, but it's exactly what happens in this band theory for two-dimensional materials. So this is a plot, just a simple plot of the Barre curvature as a function of G1 and G2, and there's a monopole here, right? This is +1 is for the upper, and -1 is for the lower, and so there's an actual monopole here, and this is actually well known once you think about it. So what's happening is there's a phase transition, a quantum phase transition, which is different than a classical phase transition. In a conventional classical phase transition, the standard machinery is the Ginzburg-Landau theory with notions of symmetry breaking, order parameter, and correlation length. That's the machinery that's used. If you consider a ferromagnetic material above the critical temperature, there's no magnetization. The moments are random. But below the critical temperature, rotational symmetry is broken, and there's a non-zero order parameter that develops, the magnetization. But not all phase transitions, now people realize, can be described in this way. In fact, a quantum phase transition occurs at t equals 0 when some parameters in the Hamiltonian are varied, like I've showed. And distinct phases may appear depending on the parameter values. And the phases are described by different values of a topological invariant. Right? This is a conventional picture now. So, this is a very busy slide, and I apologize, but it's got a lot of very good stuff. So here's a Schrodinger equation, and what I'm trying to get at here is there's this quantity called the quantum geometric tensor, and there's this idea of quantum parallel transport. So let me just describe to you what parallel transport is. I am standing here, and there's a sphere around me, and I'm going to show you parallel transport in a sphere. This is a vector, and I'm going to parallel transport this vector on the surface of a sphere. It's up, right? I go up, around, then I go this way, and then I go that way on the sphere, and the vector is now pointing in a different direction than I started because it's a curved space. So there's this idea that of parallel transport in parameter space. So let me describe this. So here's the Schrodinger equation, which depends on some parameters. And this is the Barre connection, which we've talked about. It's just the gradient with respect of the derivative with respect to S mu of some state. And there's this idea of a gauge covariant derivative, which means you have some state and you have a phase here, and this gauge covariant derivative behaves in a way where you can actually pull the phase out, shown here, and is just given, the result is just given by the gauge covariant derivative here. What is the gauge covariant derivative mathematically? It's shown here. It's just a fancy combination between the derivative with respect to one of these parameters of the state psi plus the Barre connection times that state. And what we have, so this is the analog of a covariant derivative in Riemannian space, except we're in a parameter space in quantum mechanics. And we can define parallel transport in the parameter space, the space of these S's, as psi of S inner product with this gauge covariant derivative on psi of S being 0. That's the definition of parallel transport. And now that we have this concept of this gauge covariant derivative, there's this quantum geometric tensor, and just bear with me because we're almost there. It's just the gauge covariant derivative with respect to mu on psi, inner product with nu, and the tensor is mu nu. So you can write that, and the importance of this is that it has two parts. It has a real symmetric tensor in the Riemannian space of parameters, that's G mu nu, and the imaginary part, so this is the real part, the imaginary part is an antisymmetric tensor, which is the Barre curvature. So this has some very deep meanings in quantum mechanics. Previously, this thing was called the Fubini study metric in the 1904-1905 timeframe. So anyway, the quantum geometric tensor has an imaginary part, which actually measures the distance between psi, a state at parameter value S and a state at psi plus delta S. The distance between those quantities in parameter space is measured by this natural metric. And this, of course, we saw gives you a Barre phase when it's integrated over space. And the importance of this metric is that in the thermodynamic limit, continuous phase transitions are known to occur when this thing has singularities, when you move these parameters around. So this Riemannian metric is the real part of this. The imaginary part, twice that, is the Barre curvature. So you can calculate all this for the 1-qubit tensor, and it looks just like this. It's a kind of a messy matrix, but the point is this. The point is that people have discussed this quantity called the fidelity, the distance between psi at S and psi at S plus delta S. It's equal to this metric tensor that we talked about, integrated and summed over these indices. So that's a fidelity. And then the Barre phase, we've already talked about, is just the integral of the Barre curvature. So there is a singularity in the quantum geometric tensor, and following the work of these folks, you can integrate, you can take the integral of the trace of this metric tensor, so here's the trace, integrated over the parameter space, and I'm plotting that on the y-axis versus E. E is where the phase transition is. And notice that there's a discontinuity. So that simple 1-qubit model has these very pretty features. You can see the phase transition in all its glory, and you can calculate it, almost analytically. I mean, it's exact. And I've already shown the Chern number is the integral of this. So now what I'd like to describe is two things. Two types of sensors that one is based on the real part of this quantum geometric tensor, and another slide will be a quantum sensor based on the imaginary part. So there's the fidelity, which we just talked about, is that given by in terms of this metric, and you can linearize these coupling constants. This is a little bit messy, but basically this formula, from this formula you can derive the phase in terms of the coupling constant in terms of the gap and 1 minus f. If you can measure the fidelity experimentally, the overlap between two quantum states by interference, if you can measure the fidelity and you know what the gap is and the coupling constants, you can then obtain the phase, essentially by knowing this Riemann metric tensor. So, so if you can experimentally measure this, you can have a quantum sensor. And if we're talking about basically in parameter space, I'm sorry, this is G1, and this is G2, the real and imaginary parts. We're talking about you move these coupling constants, so you have some physical system where you're able to move these coupling constants, right, by some external fields. And you move them, and as you move them, you're able to do essentially perform the operation of sensing. How quickly? You have to move them slowly, because if you move them too fast, there's a measure of adiabaticity. Delta E is a gap between upper and lower states. And if this quantity is small, how quickly you move these parameters, these are the velocity of the motion of the parameters, this quantity has to be essentially small in order for this whole thing to hang together. So the slower the parameters vary, the smaller the energy uncertainty, and the system stays in the same energy level you started with. Okay, so now we can talk about another case where you have a sensor based on the Barre curvature, which is the imaginary part of this. And so you can measure the Barre phase in two different ways. One is a traditional interference method, where I'm imagining you have a magnetic field along Z, a magnetic field along X and Y, and this is the position of the field vector, and you can move it around in a circle, right, in the XY plane. So an external parameter like the magnetic field can be changed adiabatically along a closed path, this circle, by varying this angle phi. This is just, and then the Barre phase can be measured through interference signal between the original state and the one state, the other copy of the state where you took it through a closed path. So that's sort of a traditional measurement method. On the other hand, there's this idea of a so-called dynamical quantum Hall effect described by Gritsev and Polkovnikov in 2012, where you can change an external field along Hx, like with speed dHx dt, and you can, for example, move it linearly in time with some velocity here, and measure the response of the magnetization along y. And then there's a linear slope, so which is the Barre curvature. So you can measure that slope. So Gritsev and Polkovnikov have defined this generalized force m, which is the derivative of the Hamiltonian with respect to any of these parameters, its expectation value in the ground state. So this is a generalized force, and essentially there's a linear response in parameter space. This is the generalized force, there's a constant, and this is the Barre curvature times the rate of change of these parameters. So if you can measure this, if you know how quickly you change these parameters, you can measure the slope. So here's an example of where I can, for example, well, I can just move the field along X. So I can move the field along X like that. This is showing movement in a circle, but if I move it just along X, I can derive the following formula. The magnetization along Y is a linear function of the rate of change of the field along X. And it's a linear, and the slope, if I can measure that experimentally, that's the slope gives me the Z component of the Barre curvature. So I can take this equation, and if I know the Barre curvature, and this is hx squared plus hy squared, and I can control those, and I don't know hz, I can measure this, I can control this, I can then determine what hz is. And this has been done in experiments with qubits of different sorts. So basically this is a sensor, a kind of a quantum sensor that is based on Barre curvature measurements, but kind of indirect. So so why look at topological aspects of quantum problems? Well, the physical properties can be characterized by a topological invariance sometimes, like in the case of the Hall effect. The topological invariants characterize an equivalence class of Hamiltonians, like in condensed matter physics. So to summarize, you can use Shannon mutual information and Fisher information to characterize the quality of a conventional quantum sensor. These quantities haven't been popular with experimentalists because they don't like to talk about information measures. But I think they're very good measures, especially when you have multiple peaks, like we've shown. And sometimes entanglement can hurt you, like in a 2-qubit sensor. And topological quantum sensors, I think this whole idea needs work, but I think you can see that there are analogies between like these 1-qubit, 2-qubit models. And to look at some of the topological properties of the 2-qubit model would be very interesting. And I gave an example of essentially kind of a quantum sensor on based on the real part and also on the imaginary part of the quantum geometric tensor. And it might be possible in some way to classify quantum sensors, maybe defined by physical invariance. For example, 2 different Hamiltonians might have similar invariance. And you would say, well, they're kind of the same in a sense of a quantum sensor, how good they are. So that's all I have. Thank you. Yeah.
Okay, thank you very much. Do we have any questions or comments? Yes, there is one here.
You started from interferometers. That means you have photons, which don't feel magnetic field very much. How would you envisage application of the sensor, assuming that you solve the problem of zero temperature? But
right. So if you have an interferometer, for example, like this Mogg-Zehnder interferometer, you could have an electric field. This could be an electric field, and this could be a piezoelectric substance, and then you create a phase shift. So then you could essentially, by counting photons, you could figure out what the electric field is. And maybe even if you have a magneto-optical substance.
Okay, but then you have some polaronic whatever effects in these crystals. Your Hamiltonian is getting much more complex.
Right. But all I have written in the case of this problem, I solved this problem analytically. For these different kind of input photons, I was able to calculate analytically these how many photons come out and the probabilities of them as a function of phi. So this was all completely quantum optics analytic calculation.
No, that's okay. This I like very much. You can say that this is not a crystal, but this is just an atmosphere over some range, if you can interfere to beams. But if you have electrons or any electrons in solidity to have any topological properties, you have some band structure properties, which means you need a solid 2D, 1D, 3D.
Right.
Then you have more complex situation too.
Right. So that's why I dreamed up this 1-qubit Hamiltonian, because it was sort of the simplest analog of this K.P theory of a topological material. The Kx, Ky are the analogs of G1 and G2. So it's sort of just a mapping mathematically, and then I started thinking more of, well, what's the implication towards sensors? And I still don't have the idea. Don't have it. I don't claim to really understand what are the implications. I think somebody should look at the 2-qubit sensor from some of these topological ideas and see what are you getting, just as a toy model, because you can solve this maybe exactly.
Okay. More questions?
Could you go back to the slides where you have the metric singularity importance in? So in general relativity, we are taught that singularity of metric is not necessarily a bad thing. Maybe it's just a bad coordinate choice. Now here, I understand the coordinates are the parameters themselves of the model.
Right.
So I don't know, how can you I don't know how to construct the question now, but how can you tell if this singularity of metric is just, well, bad parameterization of parameter space?
Right. So,
Over,
but
like
these in the quantum problem, these parameters play I think a more central role because it's the Hamiltonian and they're really there. It's not like you're going to make a coordinate transformation and transform the physics away.
Yes.
Well, like in general relativity, nobody observes coordinates. They're not observable, right?
Right.
And so you can transform and use any coordinate system. Here, the Hamiltonian is sort of, it is what it is. And those are the fixed parameters that you can vary. It's a slightly different conceptual.
Yes,
idea.
I understand. I wonder, since you raised this question of classification, well, there are some methods, again, coming from decomposition of Riemann tensor and so forth and on. Maybe there's also something in that direction.
Right.
Just the difference.
It would be interesting to see, let's say, within something more complicated than one qubit, like the 2-qubit model, if you could show something like that.
Right.
There's also what's very strange is in these plots where I said that there's a crossing here. If you look in the G1, G2 space, this energy band crossing, there's a group theory argument to be made about what's going on. They're called nodal lines in solid state theory. And so there's some nodal lines going on, and I'm not even sure what role they play here, right? And I don't even know what group they are. I haven't figured out how to do that, right? But these analogies are there, and I'm staring at them.
Yes, indeed.
Very tantalizing, especially because it's exactly solvable.
Okay, anyone else? If no, let's thank once again.
Thank you. It's my pleasure.